All right, homework 8 is actually now starting chapter 4. It says making reasonable inferences based on proportion statistics. In other words, we're just basically going to take a proportion, a fraction, change it to a percent, and then answer the question based on that. It says in a study of pain relievers, 20 people were given product A, and all but 7 experienced relief. In the same study, 100 people were given product B, and all but 21 experienced relief. Fill in the blanks for the statement, product what performed better in the study because what percent got relief with this product, whereas only this percent got relief with the other product. So we're looking for the percent that got relief. We had 20 people, all but 7 experienced relief. So how many people experienced relief? 20 minus 7 would be 13, right? 13 out of 20 experienced relief. What percent is that if you figure that out?
A lot of times,
65%, exactly. If you divide 13 by 20, you get 0.65, 65%. Second part of that, we had 100 people, all but 21 experienced relief. So how many actually did experience relief? We take 100 minus 21, we get 79. And since that's already out of 100, we hopefully know that 79% got relief, right? So, which one performed better, product A or product B? Product B did, because 79% got relief. Whereas only 65% got relief when they used product A. Okay? Second one of that one, it says the records of a computer retail store show that out of 100 customers who purchased a desktop computer last month, 69 also purchased the service plan that extends the warranty. Out of 50 customers who purchased a notebook computer last month, 40 purchased the same service plan. Fill in the blanks. So the last month, customers of the store who purchased what kind of computers were more likely to purchase the service plan because what percent purchased the service plan, whereas only what percent of the other ones bought what kind of computers purchased the service plan. So we're looking for the percent who purchased the service plan. On our desktop computers, 69 out of 100 purchased the service plan, which is 69%. We already knew that. It's nice when they do out of 100. On our notebook computers, for our notebook computers, we had 40 out of 50 that purchased the service plan. 40 out of 50 is 80%. So, which purchasers were more likely to purchase the service plan? The people who bought the notebook computers, right? The notebook purchasers were more likely to purchase the service plan because 80% of them bought the service plan. Whereas only 69% of the customers who bought the desktop computers purchased the service plan. So on number 3 there, in a recent study, 100 males used a new weight loss supplement, and all but 28 of them experienced weight loss after 2 weeks. In the same study, 25 females used the same supplement, and all but 3 of them experienced weight loss after 2 weeks. So we're going to fill in the blanks. The new weight loss supplement was less effective on who? Because in this study, what percent of them failed to lose weight after 2 weeks? Whereas only what percent of the other ones failed to lose weight after the 2 weeks? So we're looking for the percent that failed to lose weight. So on the males, how many of them failed to lose weight? 28 out of 100, right? 28 out of 100, which is 28% of our males. For our females, how many failed to lose weight? 3. 3 out of the 25. 12%. So, the new weight loss supplement was less effective on I gotta read that one again. All but 20 of them experienced, oh, we got those backwards. 28% of them, all but 28 of them experienced weight loss after 2 weeks. So all but 28 of them, okay, that was failed. Did I write this backwards when I wrote it down? In recent 100 males used a new weight loss supplement. All but 28 of them experienced weight loss. So 28 of them, all but 28 of them.
Yeah, so 28% experience,
Okay.
so it was effective on 28% of them.
So 28 of them experienced weight loss.
And then only
12,
12%
okay.
was effective.
So it was less effective on the males because 28 of them failed to lose weight, right? 12% of the women failed,
Oh.
right?
Okay.
That's where I'm getting messed up.
Okay.
I knew it was some crazy thing. So it was less effective on the males, even though the 28 is higher, but we're looking at how many failed to lose. A higher percent failed to lose weight, right? Whereas only 12% of our females failed to lose weight. Alrighty. Yeah, sometimes they word things crazy and you're like, what in the heck? Factorial expressions. A factorial expression is basically you're going to take the number times every number smaller than that down to 1. If I'm doing 8 factorial, it means I'm taking 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, they want to make your work a little shorter. If I think about 8 factorial divided by 5 factorial, 8 factorial would be 8 times 7 times 6 times 5 factorial, right? The 5 factorials could cancel each other out there. If I have it the other way around, I have 8 over 10. The 10 is bigger. I'd have 10 times 9 times 8 factorial. So the 8 factorials could cancel each other out. Because you probably don't want to have to go 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 and then do it again. So if I can take my values here and start with the bigger one until I reach that smaller one, then I can cancel out the smaller one. So we're going to calculate on the top. If we do 8 times 7 times 6, we would get
336.
336. On the bottom, we just have 10 times 9, which is 90. And then we have to reduce our fraction down to simplest form. So if we reduce that down, we're going to get
Maybe 3.
we can divide by 3, yep.
Maybe 3 as a whole number. And
If I divide by 3, I'm going to get 112 over 30, right? But I can reduce that some more.
I'm not following.
10. Oh wait. I don't know if you can do 10 without getting a decimal, right? I'm going to keep it
No,
a whole
because that
number.
3 goes into 112, does it? But 2 goes into both of them. I can divide by 2,
Yeah.
right?
So 56 over 15.
And then I think we're stuck. All right. So, if I have 8 factorial divided by 5 factorial, 8 factorial means I'm going to do 8 times 7 times 6 times 5, 4, 3, 2, 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. So what we did is took the bigger number, started listing our values until we hit the bottom one, because then we could cancel. On the second fraction, the 10 was bigger than the 8. So I started with the 10. 10, 9, 8, and then I could cancel out my 8s. So then we just multiplied the top and the bottom and simplified our fraction. Now we probably could have simplified our fraction here before we multiplied. We could have reduced the 8 with the 10 and so forth and made it a little easier. So on number 5, 11 factorial is bigger than 8 factorial. So we're going to say 11 times 10 times 9 times that 8 factorial, which is then going to cancel out, right? On the other one, we have 7 and 6. Well, we would have 7 times 6 factorial, and the 6 factorial is going to cancel out. So what we end up with is 11 times 10 times 9 times the 7 from the other one, right? Which gave you
6,930.
6,930, nothing left on the bottom. So on number 6, notice here the 8 is the bigger one, right? So I'm going to make that 8 times 7 factorial, which is going to cancel out my 7 factorials. If I simplify that first part of that fraction, I'm just going to have the 8. If I have the 11 with the 8, I'm going to say 11 times 10 times 9 times that 8 factorial that I'm going to be able to cancel out. So on the top of my fraction, I have 11 times 10 times 9.
No, 990.
990. On the bottom, I just have an 8, and then I want to reduce my fraction down. I know I can divide by 2 anyway.
It'd be 495 over 4.
495 over 4. Can't simplify it any further than that. Combination. A combination, the order doesn't matter. If I have red, green, blue, or blue, green, red, it counts as the same thing. The order isn't important. We have a formula for combination. They're going to say it looks something like this. If I have a combination of n things taken r at a time, that I am going to do n factorial over r factorial times n minus r factorial. So on number 7 it says, how many ways can 6 letters be chosen from J, K, L, M, N, O, P, Q, R, S? Assuming that the order doesn't matter and repeats are not allowed. So what I'm saying is I'm going to find the combination of, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things on my list, and I'm going to choose 6 out of those 10. So if I put that into my formula, I am going to have 10 factorial over 6 factorial times 10 minus 6 factorial. And 10 minus 6 then would give me 4 factorial. So I'm going to think of it this way. I'm going to start with my bigger number again, and I'm going to use the bigger of these two, which is the 6. So I'm going to go 10, 9, 8, 7, 6. The 6 factorial is going to cancel out. On the bottom, I still have the 4 factorial. So I'm going to have 4, 3, 2, 1. So on the top, I'm going to take 10 times 9 times 8 times 7. On the bottom, 4 times 3 times 2, and the 1 really won't make a whole lot of difference. On the top, I would get
5,040.
5,040.
Yep.
On the bottom, I'm going to get
24.
24. That should divide in there nicely.
210.
210. There are 210 different ways that I can choose 6 letters from that list of 10. So number 8, in how many ways can a committee of 13 be formed from 17 people? Assume that when people are chosen from my committee, the order does not matter. So if the order doesn't matter, I'm doing a combination. I have 17 total people. I'm going to choose 13 out of that 17. How many different ways can I do that? So 17 factorial over 13 factorial, and then I'm going to have 17 minus 13 factorial, which is 4 again, right? So if I'm figuring that out, 17 times 16 times 15 times 14, and then the 13 factorial is going to cancel out. And then on the bottom, I'm just going to do the smaller one, the 4 factorial. So 4, 3, 2, 1 again. On the top, we would get 57,120. On the bottom, we probably got 24 again. So when we divided 57,120 by 24, 2,380. So there are 2,380 ways to get a committee of 13 people if I have 17 to choose from. Number 9, from a group of 17 customers, 5 are to be chosen to receive a special gift. Assuming that the order in which the customers are chosen is irrelevant, does not matter, how many groups of 5 can be chosen. So again, I'm going to do a combination. I have 17 total customers. I'm going to pick 5 out of that 17. So 17 factorial over 5 factorial, and then I'd have 17 minus 5 factorial, which would be 12. So if I were picking, I would go down to the 12 and cancel it out, because that'd be easier than going down to the 5. So 17, 16, 15, 14, 13, and then my 12 factorial is going to cancel out. I still have to do the 5 factorial, which means on the bottom, 5, 4, 3, 2, 1. So on the top, I ought to have a nice big number.
742,560.
742,560 on the bottom.
120.
120. And if I take 742,560 divided by 120, I get
6,188.
6,188. Now, you are going to have a technology activity, but I'm going to give you a preview. We can do combinations and when we get to permutations on our calculator. When we do them, you want to be on the home screen. So press second and mode, which is the quit. Second mode. So you're just on the regular screen where you could type in a math problem. We are going to put in the first number. I'm going to do number 9. So I'm going to put the 17 in first. 17. Then I am going to hit the button that says math. It's right under the green alphabet, or yours isn't green because you got that one, but it's the third one down under the y equals, or fourth one down, third one after the y equals anyway. It says math on it. See the one that says math? Hit math. Under math, we are going to cursor over to the one that your older calculators probably says PRB. On the new calculators, it says PROB for probability. Hopefully you see that choice number 3 says NCR. So I'm going to pick number 3. Now you'll notice there's a little 17 with the C, and then I got to put in the R. The R was 5. And if I hit equals, hey, we get 6,188, right? So, okay, hit equals. The enter button. There it is. So, you'll have a technology activity. It's going to give you these directions, but I just wanted to preview that with you when you get there. Permutations. Permutations, the order matters. It's like picking a president, a vice president, and a secretary. It's different if I pick me for the president and Leanne for the vice president and Mariah for the secretary, or if I went in the reverse order and made Mariah the president and you the vice president and me the secretary. Those are two different things. So when you have a permutation, the order matters. Formula for permutation. Again, if I have n things and I'm taking r of them, I'm going to have n factorial divided by n minus r factorial. So suppose that a code consists of 4 digits, none of which is repeated. A digit is one of the numbers, 10 numbers from 0 to 9. How many codes are possible? So 1, 2, 3, 4 is different than 4, 2, 3, 1, right? I'm going to do a permutation. I have 10 digits to choose from. I'm going to do 4 of them. So I am going to do 10 factorial over 10 minus 4 factorial, which would simplify into 6 then, right? Same thing, instead of going all the way from 10 down to 1, I'm just going to go to 6 factorial. So 10 times 9 times 8 times 7 times 6 factorial, and then I can cancel out the 6 factorial. And so we're going to end up taking 10 times 8, 10 times 9 times 8 times 7. 5,040. Number 11, a company has 11 salespeople. A board member at the company asks for a list of the top 5 salespeople ranked in order of effectiveness. How many lists are possible? Assume that the order of the salespeople on the list is relevant. It makes a difference who's first, second, or third. So, again, we're doing a permutation. We have 11 salespeople. We're going to do the top 5. And so we're going to do 11 factorial divided by 11 minus 5 factorial. 11 minus 5 will give us 6 factorial, right? So starting with the 11. 11 times 10 times 9 times 8 times 7 times, there's my 6 factorial that I'm going to be able to cancel off my list. So we end up taking 11 times 10 times 9 times 8 times 7, which is 55,400, did you say? And 40. Number 12, 14 athletes are running a race. A gold medal is to be given to the winner, silver to the second place, and a bronze to the third place. Assuming there are no ties, how many possible ways can the 3 medals be distributed? So again, the order is important. First is different than second, which is different than third. We're going to do a permutation. 14 people, we're giving out 3 medals, first, second, and third. So 14 factorial over 14 minus 3 factorial, which would be 11 factorial. So we're going to have 14 times 13 times 12 times our 11 factorial, which is going to cancel out. 2,184. Now, much like your combination, we can do the permutation in the same way. We first are going to start by putting in that first number. I'm going to get back on my home screen if I'm not on there already. So it doesn't matter if you have the other one in there. You can clear out your home screen if you want, but it won't matter. I'm going to put the 14 in first. I'm going to hit the math button. I'm going to cursor over to the probability. And number 2 is your permutation choice. Once I have that on my screen, I'm going to put in the number for how many I'm choosing. In this case, 3. And if I hit enter, I should get 2,184. Math, cursor over to the PRB. Number 2 is your permutation, and then put in your 3 that we were using for R and enter. 2184. You have directions under your technology stuff in your big binder of whatever on how to do that. All right. Now we are going to do permutations, combinations, and the multiplication principle for counting. The multiplication principle of counting, that's also called the fundamental counting principle, says that if I can do things in 3 different ways, or 3 different things, I take the number of ways of the first, the number of ways I can do the second, times the number of ways I can do the third, and I just multiply all those together to get my total number of ways. They're going to mess these all together. First one is actually going to be our fundamental, our multiplication principle for counting. Serial numbers for a product are to be made up of using 2 letters followed by 2 numbers. If the letters are to be taken from the first 7 letters of the alphabet with no repeats, and the numbers are taken from the digits 0 through 9 with repeats, how many serial numbers can be generated? So the fundamental counting principle just says if I take the number of ways of each of those possibilities times each other, I'm going to get the total number of ways I can get my combination. So my first one, I'm going to use a letter. I'm going to use one of the first 7 letters of the alphabet, so that means I have 7 choices there, right? My second one, I'm going to use the first 7 letters of the alphabet, but I can't repeat what I used for the first one, so that means I only have 6 choices of what I could use for that one. Because I can't repeat. If I already used the first one, now I only have 6 left over, right? On my third one, I'm going to use the numbers taken from 0 through 9, which means I have 10 possible choices. So I have a 10 there. Now we can repeat on our numbers. So again, we're using 0 through 9. I have 10 choices here. So in order to find my total possibilities, I'm going to take my 7 times my 6 times my 10 times my 10. 4,200. Now they're going to use that fundamental counting principle with combinations and permutations by figuring out the answers and multiplying the 3 or how many ever things together that I'm going to do. I have 3 research departments have 10, 8, and 7 members respectively. Each department is to select a delegate and an alternate to represent the department at the conference. In how many ways can this be done? So, first thing I have to decide, am I doing a combination or a permutation? Combination, the order does not matter. Permutation, the order does matter.
A combination.
Try the other one. Permutation. Because it's different if I have who's the delegate and who's the alternate, right? If I switch those around, that would be a different way. So it's a permutation. So we're doing permutations on this one because the order does make a difference. So we have 3 departments. The first department has 10 people. I am going to choose 2 of them, 1 delegate and 1 alternate, right? Then I'm going to do the next department. It has 8 people. Again, I'm going to pick 2 of them, 1 delegate, 1 alternate. Then I am going to have my next one, which is 7. Again, I'm going to choose 2 of them. For fun, instead of doing the long way, we're going to use our calculators because that's why we're learning how to use our calculator. So, we got to calculate a permutation of 10 things taken 2 at a time. So we're going to put in the 10, hit the math button, number 2 for permutation, and then put in the number 2 for 2 at a time. What do we get for our answer if we do that? I worked it out the long way on my paper, but we'll use our calculator. 90. Getting 90 land? Yep. And number 2. And then we're going to put a 2 and enter. There's your 9. Okay, now we're going to do the second one. The second one, we're doing a permutation of 8 total people. We're going to take 2 out of that 8. $56. The third one, we're going to have 7 people, and again, we're taking 2. $42. So now, based on our fundamental counting principle, or the multiplication principle for counting, I'm going to take my 90 times my 56 times my 42. I get
Was that 50? Or
56, 90, 56, and 42. 211,680. So I have 211,680 ways of choosing those groups of people. Number 15. A catering service offers 5 appetizers, 11 main courses, and 3 desserts. A banquet chairperson is to select 3 appetizers, 8 main courses, and 2 desserts in a banquet. How many ways can this be done? So if I'm picking out appetizers, does it matter if I take my fried pickle before my French fries before my onion rings? It's the same group, right? So I am going to do a combination instead of a permutation this time. The order doesn't matter of my 3 appetizers. It's the same group of 3. Doesn't matter which order they're in. So we're going to do combinations. We had 5 appetizers to choose from. We are going to select 3. For our main courses, we had 11 to choose from. We are going to select 8. And for our desserts, we had 3 to choose from. We're going to select 2. And again, unless you really wanted to work it out the long way, we'll just use our calculator. Same thing as when you did permutations, only now we're going to do choice number 3 to do a combination. So we're going to start by putting in the 5, hit the math button, do the probability, choice number 3 for combinations, and then 3, and what do we get there for the first number? 10. On the second one, we're going to do a combination of 11 things taken 8 at a time.
165.
165. And 3 things taken 2 at a time, we get 3. And then for our fundamental counting principle, we're going to take the 10 times the 165 times the 3 to get our total number of ways.
4,950.
4,950. All right. Venn diagrams. A Venn diagram is a way to kind of draw out what's happening. In this case, we have a sample space of S. Notice they put an S up here. That's the whole thing that I'm considering. P and Q are events in my sample space. When I put the bar above it, I want to shade those things that are not in P. So if I'm going to shade those things that are not in P, I'm going to shade everything but that circle that is P. So what you're going to do is click in all those regions so that everything but this circle that's P is shaded, right? A bar over it means it's not in that section. I want to do not in P. Everything that's not in P. Now we're going to add in the union and the intersection symbol. The union symbol, if you remember from algebra, meant or. If it's or, it can be in this set or this set, so I can put it both of them. If it's the intersection, it's the word and. And means it has to overlap in the middle. So this means that it's not in Y or X. The bar over the top means not, and then it's over the Y or the X. So if it's not in Y or X, where would I shade?
Just the outside?
Just the outside, right? I don't want either of my circles shaded anywhere. I'm on the outside of Y and X. So anything that's not in Y or X. So number 18, we want to do B and not C. So I want to shade B and not C. B would mean I would shade this circle here. But since it says and, I have to do the not C. If I don't want to shade C, I don't want to shade this section here. So if I'm going to shade B and not C, I am just going to shade this part of my circle for B. If I just shaded B, I'd shade that whole circle, but I want to not shade the C part of that circle. So they'll do some shorter ones, and then once you get used to all that weird stuff, you'll get some longer ones. So now we've got more circles within circles with all over the place craziness. It says, among adults denoted by A, there are those who enjoy coffee, the C's, and in particular those who enjoy espresso, which is the E. Coffee drinkers are neatly divided into those who grind their own beans, denoted by B, and those who don't. So A is all of our adults. C is our coffee drinkers. In the coffee drinkers, we either have those who enjoy espresso or grind their own beans, or in the middle, both. So it says, represent by shading the appropriate region of adults who either do not enjoy coffee or enjoy espresso after grinding their own beans. So since this is an or, we're going to shade them each separately. If I do not enjoy coffee, where would I shade? I would shade all this part on the outside of the coffee circle, right? All the A part outside of the coffee. So we've got the part where they do not enjoy coffee. Now we want to do enjoy espresso after I ground my beans. So that means they have to both enjoy espresso and grind their beans. So where would I shade for that? Right here in the middle, where E and B overlap each other. Those people both enjoy espresso and grind their own beans. Ooh. Number 20, among high school graduates denoted by the H, there are those who studied algebra with the A, those who studied geometry with the G, and those who took music appreciation with the M. Represent by shading the appropriate regions those high school graduates who studied either algebra or geometry, but not both, and in addition took music appreciation. That's going to be a really small section, right? They have to have studied either algebra or geometry and took music appreciation. So if I did algebra or geometry, but not both, here's my algebra section here. Here's my geometry section. I don't want the both, right? So I know I'm starting here or here. But in addition, I have to do the music appreciation. Of this section, these ones studied music appreciation, and these ones studied music appreciation. So this little section here and this little section here would be those people who studied algebra or geometry and also took music appreciation. That makes sense? Kind of, maybe. #21. All American high school students study American history, denoted by H. Some also study world history, denoted by the W, and some study English history with the E. So represent by shading the appropriate regions those high school students who either studied all three branches of history or study only American history. So if it's an or, we can do them both separately. Where would I shade for those who studied all three branches of history? All three of them. Where would they all intersect? Right here in the middle. So right here in the middle, I'm representing all three of them. They're in the history, they're in the world history, and they're in the English history. Or, what's the other part? Studied only American history. If I studied only American history, where would I shade? Which section is the only American history? The H section, not inside those two circles, right? So the H section would be the only American history. And then we get to make them even crazier, because now we're going to do all the symbol things with the intersections and the unions and the not symbols. So, A, B, and C are events in my sample space S, which are represented in my Venn diagram below. Indicate by shading the appropriate regions of the Venn diagram. So I am going to do A. This means and, not C. Again, we have an and. B. When we have and, it means they all have to overlap each other. So we want to figure out if I have A and not the C and the B, where we could shade. You're exactly right. This top little section right here. That has A, but not the C, and also has the B. if I'm in that section. I'm in the A and the B, but not the C. A, B, and C are events in my sample space S, which are represented by the Venn diagram below. Indicate by shading the appropriate regions of the Venn diagram. So here we have parentheses. We are going to do A or B, and then we have the intersection symbol, so and, not C. So A or B means we could shade all of A or all of B, but and the not C. So if I'm going to shade A or B but not the C, where would I shade? I'm going to shade here for my A and here for my B, and I'm not going to hit that C circle at all, right? Last one for today. A, B, and C are events in my sample space S, which are represented by my Venn diagram. This time we're going to do A or B and the C. A or B and the C.
All of the circles.
No. Because of the and. If it was A or B or C, we would do all of the circles. But it's A or B and the C.
So is it the outside of A and B and then that middle part, or?
Nope.
Oh.
So A or B means I would shade this circle or this circle. But we have to do the and C. Which part of those circles are including the C? Just this part, right? So we end up shading right here in the middle where that overlaps with C. A or B means I could do A or B, either of those circles, but then the and, it has to include the C in the section. The only parts that include the C, this part here in the middle. All right, those might take you some practice, getting used to all that weird stuff.